In this program, we're going to examine the diagnostics of the Saturn automatic transaxle. The Saturn 4-speed automatic transaxle is designed to provide automatic shifting with world-class smoothness. To achieve this, the transaxle features electronic controls. 5 electro-hydraulic actuators are controlled by the Powertrain Control Module, or PCM. The PCM controls the shift schedule and shift feel and provides onboard diagnostic capabilities. In this program, we will take a close look at the transaxle's hydraulic and electronic control systems. We'll begin with the hydraulic system. It consists of these components: the converter housing, transaxle case, and rear cover, the oil pump, a suction filter, and a pressure filter. The control valve body made up of an upper body, lower body, and a separator plate, the electro-hydraulic actuators, an actuator electrical connector, and a cover. The torque converter, clutches, and forward-reverse servo complete the list of hydraulic components. The oil pump is the familiar gear type. It consists of the oil pump body, a stator support, drive and driven gears, fluid passages, 1 hydraulic valve, and the thrust plate. The suction filter connects to the pump assembly. Passages in the housing and stator support align with the input shaft. The pump and suction filter assembly is mounted on the converter housing with bolts and alignment dowels. The seal rings shown here are positioned around the input shaft and separate 3 hydraulic circuits. Except for servicing the actuators and their connector, the valve body must be removed from the transaxle case for service. Let's now examine the valve body in detail. Remember, it consists of an upper and lower body separated by a plate and gaskets. We'll start with the lower body, which features these parts: the converter limiting valve, spring and retainer, the converter charge valve, spring and retainer, the TCC enable valve train, bushing and retainer, the manual valve, which is connected to the shift lever, the actuator feed mode valve, spring, plug, and retainer. Smaller parts in the lower valve body include a filter for the line pressure actuator and 2 rubber check balls and springs. While the lower body parts are probably all familiar to you, the upper portion of the valve body contains both similar and different parts when compared to conventional hydraulically controlled transaxles. Familiar areas of the upper valve body include the pressure regulator valve train, including the regulator valve itself, control and boost plungers, and necessary springs, bushings, and retainers, the detent arm and roller for the manual shaft, and a steel check ball on the underside. On the other hand, a unique new patented feature of this transaxle is the clutch priority valve, which acts as a hydraulic backup in case the electronic controls ever fail. The clutch priority valve train consists of a plug and retainer, a 3rd clutch exhaust valve, the clutch priority valve itself, and a spring and plunger. Most importantly, the 5 electro-hydraulic actuators fit into bores on the top of the valve body. The actuators are used to control the 4th clutch, the 3rd clutch, the torque converter clutch, the 2nd reverse clutch, and line pressure. The actuators themselves are all identical and interchangeable. They consist of a solenoid coil with 2 terminals, an inlet port located at the bottom, an exhaust port located at the top, outlets through openings on the sides, and an armature-type valve with a spring. On the outside, the inlet port and outlet passages are separated by 2 O-ring seals. Each actuator has 2 positions. When the solenoid circuit is on, the inlet port is blocked and the outlet port is connected to the exhaust port. In this position, fluid entering at the side outlets exits through the exhaust port. When the solenoid circuit is off, the inlet and outlet ports are connected and the exhaust port is blocked. In this position, fluid enters at the inlet port and exits through the side outlet ports. The one-piece actuator electrical connector snaps into place on the actuators. On the top of the actuator electrical connector is a plug for the vehicle wiring harness. A cover holds the actuators and connector in place and routes the flow of oil from the exhaust ports. A separator plate is used between the upper and lower valve bodies. The plate provides transfer passages, orifices, and check ball seats for the circuits. The hydraulic system has a total of 9 different circuits for line pressure, lubrication, the converter, the forward and reverse clutch, the first clutch, the second and reverse clutch, and realize that this circuit varies with the position of the forward-reverse clutch, the third clutch, fourth clutch, and the torque converter clutch. You'll find diagrams detailing the circuits in the service manual. We'll spend a few minutes right now reviewing the path of each circuit. We'll begin with the line pressure circuit. Oil from the pump flows to the pressure regulator valve and also to the line pressure actuator. The Transaxle control module, or TCM, which is part of the PCM, pulse width modulates the line pressure actuator. By varying the percentage of actuator on time, the TCM controls the pressure going to the pressure regulator valve. From the actuator, oil flows to the control plunger in the pressure regulator valve train, which controls line pressure. Line circuit oil also flows through the pressure filter to the clutch priority valve, the TCC enable valve, and the manual valve. Here is the path of the lubrication circuit. Unlike most other transaxles, oil starts at the pressure regulator valve. From there, it flows to the lube relief valve, where excess lube circuit pressure is exhausted. Let's review the converter clutch apply circuit. Again, oil flow starts at the pressure regulator valve. It then flows to the converter charge valve, which limits circuit pressure to prevent the torque converter from ballooning or expanding with high line pressure during cold temperature operation. As oil flows through the torque converter, it exits into the converter out circuit and into the oil cooler. It also flows to the converter limiting valve, which regulates TCC apply pressure to the required level to maintain TCC apply. Because the Saturn Transaxle shares one clutch for second and reverse, the forward-reverse servo is used to distinguish the two operations. When the driver moves the shift control lever into reverse, the manual valve moves. Oil flows to the transaxle case and into the forward-reverse servo. Pressure builds in the servo cylinder, moving the clutch sleeve and engaging the reverse-driven gear. When the driver moves the shift control lever into park or neutral, the manual valve moves, blocking the line circuit and exhausting the reverse circuit. Spring tension then returns the forward-reverse servo to the forward position. Now that we've seen how the servo responds, let's examine the actual second and reverse circuit. When the driver moves the shift control lever into reverse, the servo is filled. Oil in the servo moves past a check ball on the valve body and into the second and reverse circuit. Oil then moves to the second reverse clutch actuator and through the circuit. Now we'll examine the first clutch circuit. The first clutch is always engaged in all forward speeds, and no actuator is required. This makes the first clutch circuit very simple. When the driver shifts from neutral into D4, D3, or D2, line circuit oil at the manual valve moves into the first clutch circuit, which takes it to the forward-reverse servo. Oil also flows to the actuator feed mode valve and toward the first clutch itself. First, however, it passes through an orifice and check ball that cushions the increase of pressure during clutch apply. Upon returning to park, reverse, or neutral, clutch pressure is exhausted through a second check ball orifice to the manual valve. Now we'll examine the second and reverse clutch circuit when second gear will be used. When the driver shifts into any forward range, the manual valve allows line oil into the second and reverse circuit. Note that the manual valve is positioned differently than when in reverse. Unlike reverse, the oil also travels to a check ball which seats. Oil also travels to the second and reverse actuator. And when the actuator is opened or turned off, oil travels from there throughout the circuit. Let's examine the third clutch circuit. When the driver moves the shift control lever into D3 or D4, the manual valve is the source of line pressure. It moves to allow the flow of line circuit oil to the actuator feed mode valve. The valve sends oil to both the third and fourth clutch actuators. To shift into third gear, the TCM opens or turns off the third clutch actuator only, sending fluid into the third clutch circuit. The fourth clutch circuit is very similar to the third clutch circuit. When the driver selects the D4 range, the manual valve allows line circuit oil to flow to the actuator feed mode valve, which again sends it to both the third and fourth clutch actuators. To shift into fourth gear, the TCM opens the fourth clutch actuator only, which sends oil throughout the fourth clutch circuit. So the difference between the third and fourth clutch circuits lies in which actuator is operated. Now let's examine the torque converter clutch circuit. The transaxle control module works the TCC release by pulse width modulating or cycling the converter clutch actuator during initial apply. The TCC actuator operates opposite of the clutch actuators. When the actuator is on, TCC is on. When the actuator is off, TCC is off. To completely engage the TCC, the transaxle control module turns the actuator on continuously without pulsing. During deceleration, the TCM may again pulse the converter clutch actuator so that release pressure is only slightly less than converter clutch apply pressure. In this way, the transaxle control module is ready for a quick TCC release if necessary. The Saturn automatic transaxle will revert to hydraulic priority or hydraulic backup in the event of an electronic malfunction. Specifically, it will revert to hydraulic priority operation if any two actuators send oil pressure to their clutches at the same time. When the transaxle is in the D4 or D3 range, this problem is resolved by the clutch priority valve, which will allow operation in the higher of the two gears. For example, if the second reverse and third clutch actuators are both attempting to apply clutches, the clutch priority valve will allow operation in third gear. Or if the third and fourth clutch actuators work simultaneously, the clutch priority valve will allow operation in fourth gear. In either situation, the valve will also prevent torque converter clutch application. If all the actuators are affected by an electrical failure, the transaxle will revert to complete hydraulic backup. Maximum line pressure will be created, causing harsh clutch apply. The park range operation is normal. Reverse is normal with harsh apply. The neutral range is normal. D4 and D3 ranges will provide fourth gear with harsh apply and no TCC operation. D2 range is normal with harsh apply. And finally, the service engine soon and shift to D2 warning lamps will light to alert the driver. We'll discuss these lamps in greater detail later. This concludes our video examination of the Saturn automatic transaxle's hydraulics. We'll now examine the electrical system of the Saturn automatic transaxle, beginning with a look at its components. The electronic brain of Saturn's engine and transaxle is the Powertrain Control Module, or PCM. The PCM itself is located under the dash on the driver's side. The PCM is comprised of two other modules, the Engine Control Module, or ECM, and the Transaxle Control Module, or TCM. It has three electrical connectors. J1 and J2 are for the ECM, and J3 is for the TCM. Inside, the ECM and TCM are connected by a hardwired communications link, which allows them to exchange information and commands. Let's examine the Transaxle control module first. The TCM has several capabilities. It can monitor its input devices, the sensors and switches that provide it with information. It can also monitor its output devices, the master relay and the 5 electro-hydraulic actuators. It can use adaptive learning for control of its functions to compensate for normal wear on transaxle components. It can display diagnostic information through the tools of the service stall system. It can work with the portable diagnostic tool to test its functions. Its calibration can be changed when PCM EEPROM reprogramming occurs. Here you see a representation of the TCM's inputs and outputs. In addition to the master relay contacts which control power to the actuators, the TCM receives input from the shift selector switch, which is part of the neutral safety switch, the turbine speed sensor, the transaxle fluid temperature sensor, the shift mode switch, and the brake pedal switch. The ECM also receives input from several circuits necessary for TCM operation: power from the ignition switch, constant power from the battery, and diagnostic request input from the ALDL, along with data from the engine speed sensor, vehicle speed sensor, manifold pressure sensor, throttle position sensor, coolant temperature sensor, and the air temperature sensor. Some of these input circuits may also be directly connected to the TCM. The TCM receives necessary information from the engine control module over a data communications link. The TCM then uses this information for its own functions. In addition, the transmission control module and engine control module work together to produce smooth shifting. During garage shifts and upshifting, the ECM retards timing to reduce engine torque, providing smoother shifts. During coast downshifts, the ECM operates the idle air control valve as part of input to output speed synchronization. When the engine is started, the transmission control module receives ignition switch controlled power and an engine speed signal from the ECM, and it completes the circuit of the master relay coil. When the relay contacts close, power through the fuse goes to the 5 actuators. The TCM operates the second reverse clutch, third clutch, and fourth clutch actuators in one of 3 modes. When an actuator is off, no current is flowing through it. When the actuator is being turned on, full current is required to activate it. This is known as the pull-in mode. Continuous use of this much current, however, would cause extreme heat buildup and shorten the life of the PCM and actuators. Fortunately, much less current is needed to maintain the actuator in the on position once it has been activated. This mode is known as the hold-in mode. For the second reverse clutch, third clutch, and fourth clutch actuators, the TCM uses an internal hold circuit. This recycles voltage spikes from the actuators through the powertrain control module back to the actuators being held. Let's examine the actuator positions throughout the gear ranges. In the park range, the second reverse, third, and fourth clutch actuators are all holding on. In the reverse range, the second reverse clutch actuator is off. The third and fourth clutch actuators are holding on. In the neutral range, the second reverse, third, and fourth clutch actuators are holding on. In the first gear of the D4 or D3 range, the second reverse, third, and fourth clutch actuators are holding on. In the second gear of the D4 or D3 range, the second reverse clutch actuator is off. The third and fourth clutch actuators are holding on. In the third gear of the D4 or D3 range, the second reverse and fourth clutch actuators are holding on. The third clutch actuator is off. In the fourth gear of the D4 or D3 range, the second reverse and third clutch actuators are holding on. The fourth clutch actuator is off. In the D2 range, the second reverse clutch actuator is off, and the third and fourth clutch actuators are holding on. The transaxle control module uses the TCC actuator to cause the hydraulic release of the torque converter clutch. As with the 3 clutch actuators, the TCC actuator can be off with no current for TCC release, on with full current for TCC apply, and on with reduced current through a separate circuit in the hold mode to maintain the TCC apply or hold. The TCC actuator also has a 4th mode. It is pulse width modulated with partial current to produce smoother TCC applies and releases. The Saturn automatic transaxle's torque converter clutch is used in ways slightly different from other transaxles. TCC is sometimes engaged in the 2nd gear, for example. The TCC actuator will be turned on when the transaxle is in the D4 or D3 range based upon sensor information providing coolant temperature, the transaxle temperature to air temperature relationship, throttle position, and gear. The TCC actuator is controlled this way. The transaxle control module turns it off when the driver shifts into park, reverse, or neutral, in the 1st gear of the D4 and D3 ranges, and when the driver shifts into the D2 range. If the TCC is already engaged, the actuator will be turned off under these conditions. If the vehicle is in 3rd or 4th gear, traveling at low speed when the brakes are applied, if the TCC detects rapid deceleration with brake apply, if the vehicle is in 2nd gear coast, or in a low-speed 3rd gear coast, during downshifts at low road speed, during coast downshifts and overrunning upshifts when the driver reduces throttle immediately after an upshift. Note that the transaxle control module does not automatically release the TCC when brakes are applied or during coast. Instead, the TCM calculates if TCC release is required. Now let's examine the line pressure actuator and its operation. You'll recall that the TCM uses the line pressure actuator to vary the pressure of the hydraulic system line circuit. The purpose of this line pressure control is to reduce the mechanical load on the engine to operate the transaxle oil pump, while providing enough line pressure to prevent clutch slip. It's also designed to vary line pressure during shifting. This helps produce smoother shifts. Unlike the other 4 actuators, the line pressure actuator does not use a hold mode. Instead, the TCM uses pulse width modulation to control the line pressure actuator circuit. It rapidly opens and completes the circuit in cycles and varies the on time during each cycle. An open circuit with no current flow and 0% on time provides maximum line pressure. A low-duty cycle with less than 50% on time provides higher than normal line pressure. A high-duty cycle with more than 50% on time provides lower than normal line pressure. A grounded circuit with 100% on time provides minimum line pressure. All 5 electro-hydraulic actuators mount in the transaxle's upper valve body. The terminals attach to the actuator electrical connector. A harness connector allows the circuits to be completed to the transaxle control module. The connectors A and B terminals are used for the 3rd clutch actuator. C and D are for the 4th clutch actuator. E and K for the TCC actuator. F and G are for the line pressure actuator. And H and J are for the 2nd and reverse clutch actuator. The TCM continuously monitors all actuator circuits and stores codes and flags when it detects a malfunction. In addition to monitoring the internal hold and clamp circuits for the actuators, the TCM monitors the master relay coil and contact circuits. If the TCM detects a malfunction, it will store the appropriate codes and flags and may revert to hydraulic backup. The TCM continuously monitors every input and actuator circuit. If the TCM detects a fault, it will do 3 things. It will store a diagnostic code and/or an information flag in its non-volatile memory with malfunction history data. If possible, the TCM will adjust the remaining devices to maintain operation, such as reverting to conventional hydraulic operation as a backup. The TCM may create maximum line pressure, resulting in harsh shifting. Gear availability may be limited depending upon the malfunction, and the TCC may be kept in the release mode. The TCM will make these adjustments to keep the transaxle running as smoothly as possible until service is obtained. In the event of a malfunction to the throttle position, map sensor, coolant, or air temperature circuits, the missing value will be estimated by the TCM using other inputs. Transaxle operation may be slightly affected, however. Finally, the transaxle control module will tell the ECM to turn one or more appropriate warning lamps on to alert the driver of the problem and the need for service. The lamps receive power from the instrument cluster wiring. When the TCM detects a malfunction, it tells the ECM to turn on the appropriate warning lamp. The service engine soon lamp lights when diagnostic codes are stored in the TCM. In addition, service technicians can use this light to display the ECM's stored codes and flags. The Shift to D2 light indicates some kind of condition exists. Shifting to D2 will help minimize potential transaxle damage or drivability problems. Shift to D2 is also used in hydraulic backup to provide manually selected second and fourth gears. Also, this light can display the transaxle control module's stored codes and flags. The hot lamp can warn that the transaxle oil temperature or actuator temperature is too high. There are more than 60 diagnostic codes and information flags related to TCM-detected malfunctions, so we don't have time to review them in this video. But you'll find that these codes and flags should help you quickly diagnose any malfunctions in the Saturn automatic transaxle. In addition to the warning lamp operation, the TCM also uses the engine control module for interaction with the diagnostic tools of the service stall system. Through the ECM, the TCM can display diagnostic codes and information flags stored as current malfunctions, using either the service engine soon lamp, the Shift to D2 lamp, or service stall system tools. And together with the SSS tools, the TCM can display malfunction history data, display live data for monitored inputs and outputs, including adaptive values, and interact to test output functions. The TCM and ECM communicate with diagnostic equipment via terminals M and A of the ALDL connector, located in the passenger compartment under the dash. If the vehicle is equipped with an anti-lock brake system, it also uses the ALDL connector. Once the diagnostic request circuit is completed, the ECM and TCM perform diagnostic tasks. The transaxle control module will alert you to the fact that diagnostic codes or information flags are stored by displaying them on the portable diagnostic tool. Once the repairs have been completed, clear the codes and flags from both the TCM and the ECM automatically with the portable diagnostic tool. Now we'll give you an overview of the sensors and switches that provide input to the TCM both directly and through the engine control module. We'll start with the 5 sensors and switches that are fed directly into the TCM. The TCM uses the selector switch part of the neutral safety switch assembly as an input for shift control lever position. 4 pairs of contacts open or close logic circuits from the TCM in a different combination for each of the 6 shift lever positions. This input affects TCM control of line pressure, shift timing, and TCC apply. The neutral safety switch itself mounts on the transaxle case and manual shaft. It has an adjustment procedure which is performed with an ohmmeter. Another input the TCM monitors is the turbine speed sensor, or TSS. The TSS mounts on the transaxle case and generates an alternating current as the second and third clutch housing rotates. 2 wires connect the TSS to the transaxle control module, which compares turbine speed to 2 other inputs: engine speed to monitor the operation of the torque converter, and vehicle speed to determine the transaxle gear ratio and monitor clutch slip. Using this TSS input, the transaxle control module controls line pressure during and after shifts. It can adapt the timing of shifts to adjust for the condition of hydraulic and mechanical parts. These inputs affect TCC apply and release as well. The transaxle temperature sensor, or TTS, mounts in the transaxle case line circuit oil passage. The TTS is a thermistor. Its resistance changes with temperature. The transaxle control module uses TTS input to calculate line pressure, shift timing, and TCC apply. The shift mode switch, mounted on the center console, allows the driver to choose between normal and performance shift schedules. When the performance setting is chosen, a light in the shift mode switch comes on to inform the driver, and the TCM adjusts the shift schedule accordingly. This shift schedule example uses the performance transaxle used with the double overhead cam engine. When a driver selects the normal mode, the TCM provides this shift schedule with upshifts occurring at lower vehicle speeds for any given throttle position opening. When the driver selects performance mode, the TCM provides a shift schedule with upshifts occurring at higher vehicle speeds with any given throttle position. Similarly, downshifts in the normal mode occur under more engine load at a certain vehicle speed. Downshifts in the performance mode occur under less engine load at a certain vehicle speed. In addition to the shift pattern change, performance mode provides for firmer upshift and downshift feel. The TCM uses input from the brake pedal switch as a part of shift timing and TCC control. Unlike most other transaxles, the brake pedal switch does not directly affect TCC apply and release. Under certain conditions, TCC remains applied with the brake pedal depressed. There are 6 additional sensors that feed information to the ECM, which uses the data for its own purposes and also sends it to the TCM over the internal communications link. Engine speed is initially measured by the crankshaft position sensor, or CPS. The CPS signal travels to the distributorless ignition system, which receives and processes the CPS signal and sends it to the engine control module. The transaxle control module uses engine speed input to operate the master relay when the engine is cranking or running, and to compare it with turbine speed in order to monitor all clutch applies and TCC operation. The vehicle speed sensor, or VSS, mounts on the transaxle case. The VSS generates an alternating current signal as the differential case rotates. The VSS signal is sent to the engine control module, which processes it. Using the VSS input, the transaxle control module determines shift pattern along with the throttle position sensor input. Vehicle speed is also compared with turbine speed to determine the transaxle gear ratio and monitor clutch slip. The throttle position sensor, or TPS, mounts on the engine throttle body. This one's on the double overhead cam engine. The TPS signal is sent to the engine control module, where it is processed. The TCM uses throttle position to determine shift pattern together with vehicle speed. It also uses the throttle position sensor input to determine TCC apply and release together with other inputs. The manifold absolute pressure sensor is located on the intake plenum of the double overhead cam MFI engine. On the single overhead cam engine, the MAP sensor mounts on the cam cover with a vacuum pipe connection. The MAP sensor signal goes to the ECM, which processes the signal. The transaxle control module uses the MAP signal to calculate engine load, which affects the control of line pressure during shifts and steady-state operation. The coolant temperature sensor, or CTS, is mounted in the engine cylinder head. The CTS is a thermistor. Its resistance varies with temperature. The air temperature sensor, or ATS, mounts in the air box of the intake system. The ATS is also a thermistor. As you've seen, the Saturn 4-speed automatic transaxle has been designed with quick diagnosis and repair in mind, so you can get your customers back on the road quickly with maximum satisfaction.